let's go ahead and wrap up the cylindrical capacitor, which we almost finished yesterday, but we didn't quite. I think that was Gianni's fault. That Gianni. Oh no. So we got to here. Those of you that are in Calc AB, hold on, let me move mine. I got a Faraday cage set up, by the way, if you want to check it out after I'm done with my spiel.
Should I push the outside of it?
Yeah, you'll get shot. If you can stand inside of it, though, then you won't get shot. You're pretty short, dude. You might fit. So, again, if you're in Calc AB, you learned yesterday that the integral of dr over r, otherwise known as 1 over r dr, otherwise known as r to the negative 1 power dr, is the natural log of r. In math class, you'll learn that the integral of 1 over x dx is equal to the natural log of the absolute value of x, right? Isn't that what the... Yeah. And that's just because e raised to some power is always positive, right? Even if the power is negative. That's just how logarithms work. But because r, in our case, is a radius, it will always be positive, unless you can tell me how we can get negative distances, because that doesn't compute with my brain. So anyway, with that integral, and with the same steps that we use to determine the capacitance of a parallel plate capacitor and a spherical capacitor, same steps for a cylindrical capacitor, and we get that the potential difference is this guy. And since dealing with capacitance, if it's always positive, really when we're talking about capacitance, we say that we're really interested in the magnitude of the potential difference. And that's just, and again, you can get a positive potential difference if you just integrate in the other direction, right? It's going to be lambda over 2 pi epsilon naught times the natural log of big radius of the cylindrical shell, divided by the radius of the inner cylinder. And we also know that lambda is charge per unit length, right? And so if we chose a Gaussian cylinder that was the same size as our rod, as long as we're ignoring the edge effects, and it's sufficiently long in comparison to the distance between the two, then we can just say that lambda is Q over L. So we can make that substitution here so that I get the magnitude of the potential difference is going to be Q over 2 pi epsilon naught L. So Q over L, that's my lambda, times the natural log of RB over RA. And I'm going to go ahead and come over here because I have my equation, because that's what we have to do. To get capacitance, we need Q, which is just charge Q. But we also need delta V, which we need to integrate E dot dr to get. And then to get E, if we don't know it, we need to use Gauss's law to get that. But once we have all that, and I have my expression for delta V, then capacitance is just Q divided by that, or multiplied by the flipped that. So I'd multiply that by 2 pi epsilon naught L over Q times the natural log of RB over RA. And as we notice, and as we should expect, if we understand capacitance, the charge cancels. And the only things that are left are fundamental constants and quantities related to the geometry of the capacitor, right? So our capacitance here for a cylindrical capacitor will be 2 pi epsilon naught L over the natural log of RB over RA. Again, entirely dependent on the difference in the radii of the shell in the inner cylinder and the object's length. Purely a function of the geometry. Understanding that will make this lab a little more easy to understand.
So that would also be super funny because like the distance between like the ratio would be like super small and it'd be natural log of like a super small number.
Yeah.
And then epsilon naught is already super small, so it'd be super small getting even super small? No, it wouldn't be.
Well, no, because if this was super small, the smaller that distance, you'll actually get a higher capacitance.
Yeah.
Right? And that's what the lab is going to kind of walk you through today with parallel plates. But you're going to get walked through today exactly how to determine what really affects the capacitance. How can I increase it? How can I decrease it? How can I increase the amount of charge stored? How can I decrease it? What happens to the voltages when I change the dimensions of a capacitor? What happens whenever I deal with a capacitor that's connected to a battery versus charging a capacitor and then disconnecting it from the battery and then making modifications? So that's what this lab is all about. And there's always at least one or two multiple choice questions on the AP exam that will deal with stuff like that. Like the changing the area's effect on capacitance or stored energy or something like that. And remember that stored energy is electrical potential energy. Keep that in mind. I know we kind of get lost, but when we have a battery, and Mr. Kelly up there can explain this a lot better than I can because I really don't understand it. But there's chemistry that goes on in here that separates the charges. That essentially puts a bunch of electrons, it's not physically what happens, but essentially takes electrons from this side and sequesters them over on the negative terminal, right? And so you have a bunch of electrons, excess electrons all shoved together, and so they have potential energy. So they have electric potential, right? Now, I'm not going to get too much into it yet, but when Ben Franklin was laying down the law, and he was calling the positives positive and the negatives negative, and he was deciding which way they're going to assume the electric current flowed. It was 150 years before we knew what an atom was and what an electron was and what a proton was. And so physically what goes on when I take a battery and I connect it to a circuit with a capacitor or with a wire, or anyone in robotics knows this already or probably has learned about this already, or engineering in general. Engineering classes. What physically happens is electrons move from the negative terminal to the positive terminal, right? They're repelled by all the other electrons, so they feel the Coulomb force that drives them from the negative. Then they're attracted to the positive, but you need a pathway for them to get there, otherwise they don't flow. That's why no electricity is flowing right now, right? I got to connect wires to it. But, and this is the first of many times that I'll say this, and if you remember from last year in AP Physics 1 when we did our circuits unit at the end, when you were all at home and probably remember everything we talked about, especially Connor, then you remember that conventional current says that the current goes from the positive terminal to the negative terminal. That's wrong. It's not physically what's happening, but that's what they assumed at the beginning, and we can thank Ben Franklin for that. So if you got beef with that, then go back in time and have words with Ben Franklin. The thing is that it was so long after all of the initial rules were laid down and so much development had happened. It was so long before they figured out what in reality was happening. They just said, screw it. We'll just leave it. We'll just call it conventional current, right? And so conventional current assumes that the electrical current flows, the charge itself flows from the positive terminal to the negative, when in reality it goes the opposite direction. Why is it okay? Because negative charge is moving this way from an electrical, mathematical, and physical perspective, behave identically, not approximately, literally identically to an equal amount of negative charge moving this way. So if I have a certain number of positive charges moving this way and I have an equal number of negative charges moving that way, they behave exactly the same. And so that's why we can, even though it's wrong, technically, it's still useful. And because so much work had been done between the initial discoveries and development of electrostatics and electrodynamics to the time where they actually discovered what particles carried the charge, so much had been done in there they didn't want to change it all because they're lazy. And again, Ben Franklin's fault, so you can blame him. Yes, sir, with the funny shirt. Am I rubbing off on you?
Yes. So, because protons are significantly more mass than electrons, that doesn't affect the amount of work needed to...
Well, they don't actually float. That's assuming that they have the same mass or they have no mass at all. Yeah. Yeah, if you actually had protons flowing, which sometimes you do when you're talking about ions in like a gas or a fluid, then yes, they have so much more mass it would be different. But if you just said the charge, if you're just focusing on the electrical properties of the charge of the electrons and the protons, then it is identical. Yeah. But because the protons don't actually move in a wire, then that's fine, right? Then we don't even need to worry about it. And that's why they don't move in wires, because the protons are the meat of the material, the protons and the neutrons, right? They're the things that are locked in place because those are the atoms of the material. And in a solid, they don't move. They can vibrate, but they don't actually move. They don't flow through the material like in a liquid or a gas.
The protons are the wire.
Yeah, the protons are the wire, literally. Yeah. Matthew? Did you say something? Timothy? Why did I say Matthew? Is it Friday? It feels like Friday. Oh my gosh. Timothy, I'm sorry. Did you have something? Did you say something?
I like how they used to call the conductors non-electrics because they didn't understand that conductivity was happening. Like
I'm not really sure. I don't know much about
so
that.
like
It's not that old.
the electric. Yeah, you're not 300 years old.
The contrary to popular belief. No. Although I just thought about that. When I was in high school, no one had cell phones. Not even flip phones. A few students did, but no one. There was no internet at school. That's how old I am. Gosh.
Do you know Ben Franklin personally?
Yeah, we were. Here's an interesting guy, that Ben
You're
Franklin.
stupid for saying it that way. On to the truck.
1970 was 51 years ago.
There was a video like some professor at MIT saying that one day we might have computers the size of refrigerators or even desks.
Now they're the size of phones. Okay, so the lab today, I just want to give you a little bit of insight before you get started. This is going to be the laboratory setup. It's going to ask you some questions, and let's I'm going to skip part 1A. I'm not going to look at that. But look at number 2 and the paragraph above it. So we have a capacitor, we have a battery. I am recording this, so if you want to watch it again. This says keep D and A constant, so I'm going to keep the plate separation D constant and the plate area constant. Notice it's in millimeters and millimeters squared. You got to convert those when you want to calculate capacitance. Careful when you're converting areas, converting the units for area. Don't be one of those people. You know what I'm talking about. It says connect the voltmeter across the capacitor. And the reason I'm going over this initially is I want you guys to understand like literally what's going on. I'm going to take my voltmeter. I grab my voltmeter. Before it says, one of the first steps, it says check all the boxes. Check all those boxes. Here's your voltmeter. I think my battery's dying. If you've ever used a voltmeter, I might have one here. Have you ever seen one of these? It's a little meter that has the two leads that you can make your electrical measurements with. Well, by convention, we take our positive lead and we put it on the side that's closest to the positive terminal of the battery. And we take our negative lead and we put it on the negative terminal. And I don't have to put it on the plate. I can put it on any wire connected to the plate.
It's floating in the
Okay. Yes, and that's what they do. They typically float. And then the battery's not connected, so nothing's happening, right? So I'm going to follow the directions here for number 2 and the instructions above. And you're going to follow the same type of directions for the rest of this. You're going to look at several different configurations of a capacitor. So this says connect the voltmeter across the capacitor. That's the terminology we use. We put the voltmeter across the battery, across the capacitor, across the resistor, across the inductor, across whatever you're measuring. Slowly increase the battery voltage to 1.5 volts. That's all the way up. So I'm just going to slowly take that slider and slide it up. Observe changes in the following quantities as D and A are kept constant. That's the capacitor spacing and the plate area. And voltage is increased. So you're just going to put in a table. C for capacitance, Q, charge on the capacitor, which remember it's just the charge on the positive plate when we're talking the charge on a capacitor. The total charge on it will be 0. But to quantify a capacitor, we talk about the charge just on the positive plate. voltage across the capacitor, very often you'll see voltage as just a V and not a delta V. Understand that anytime you just see a V, it is a delta V. They're saying voltage across the capacitor and they only have a V. That is a voltage difference. The voltage on the capacitor, like on just the positive plate, is going to be 0 because there's no potential difference there. You got a potential difference once the capacitor is charged. So sometimes you see it V, sometimes you see it delta V. Okay, so just be prepared for that. And then E, the electric field between the plates of the capacitor. And I'll give you this way now. The electric field is where the energy gets stored. Like when we store energy in a capacitor, it's actually stored within the electric field. And it's the electric field discharging that energy that provides the electrical power. The electrical forces that drive the charges and stuff like that. And then we'll talk about that a lot more when we talk about dielectrics next week. All right. Note the observations and provide reasoning in the table on the next page. So before we look on the table, let me just increase this, and we'll see little arrows with little balls in them with negatives. So that's telling you the direction that the negative charges are moving. So notice as I turn on the battery, I'm essentially just turning on the battery. I'm closing the circuit. As I increase from 0 volts to positive 1.5 volts here, this guy gets positively charged, so he pulls electrons off of that plate, right? This guy gets negatively charged, so he forces electrons onto that plate. If this was a closed circuit, if I closed these guys with a wire, then it would just keep flowing, and I would have a short circuit, and it would get real hot, and it would burn out. But because the capacitor plate literally has space between it, the electrons can't. And so they're going to flow until they reach until there's so many electrons on this that the force this way is going to be exactly equal to the force this way, and they're not going to flow anymore. At that point, these two, the bottom plate and the negative terminal on the battery, will be at the same electric potential. And for the same reason, the top plate and the top terminal, the positive terminal of the battery, will be at the same electric potential. If you don't have a potential difference, then the charge isn't going to flow. Okay?
That's a fancy battery. You can turn that on.
It is a fancy battery, yeah. Think of it as like a power supply where you can turn up the voltage, turn down the voltage. So I'm going to raise this up, and as we would expect, negative charges, and that's what the arrows are showing. Negative charges are moving from the positive to the top plate to the positive terminal, from the bottom plate to the negative terminal. Okay. Number 2 says, as voltage was being increased, what did you observe about the motion of charges in the external circuit? Well, exactly that. The electrons move from the top plate to the positive terminal, or move from the top plate to the battery, and electrons move from the battery to the bottom plate. If you're an electrician or an electrical engineer, and you're dealing with schematics, and you're dealing with work that an electrician is going to have to actually build in a house or something, then you're assuming that the current is going in the opposite direction. That's called conventional current. Okay. Even though it's actually going the other way. So that would be your answer for number 2 there. Number 3 says, after the voltage was constant 1.5, notice that the voltage across the capacitor is 1.5 volts. The same as that of the battery. Therefore, no potential difference between these, and no chance for electricity to flow here. So now no more charge flows, right? So after the voltage was constant at 1.5 volts, what did you observe about the motion of the charges in the external circuit? The charges stopped moving. So let's discuss the 4 quantities that it asked us about and the reasoning. And there's 2 ways. I'm going to read all these. I'm actually going to grade these. When you provide reasoning, there's 2 main ways that you can provide reasoning. You can talk about the proportionalities in the equations, or you can just talk about the physical, you can use your physical understanding of the things like energy and its relationship to electric potential to answer the question. So when we talk about what happened to the capacitance, well, we can see we got the meter up here. The capacitance, it's 0.3 picofarads. As I go from 0 volts to 1.5 volts, what happens to the capacitance?
It's the same.
It's the same. Because remember, the capacitance is the capacity to store charge, to store energy. Whether or not it's storing energy or not. That was redundant.
Store energy?
Huh?
Does it store energy?
Does it store energy?
Whether it does or not, it does not.
Never mind. So yeah, the capacitance doesn't change because capacitance is a function of capacitor geometry only. And you might want to remember that for an air-filled or a vacuum-filled capacitor, the capacitance is simply epsilon naught times the area over the plate separation distance d. So nothing changed here, so the capacitance doesn't change. So you could either just say the capacitance is, according to this equation, a function of geometry only, or you could just say that yeah, you just say that and works. So that's fine. You don't need to be super long-winded. There's not enough space for that, but you can either reference the equations or just talk about your conceptual understanding. What about the charge? And we're just talking about the charge on the capacitor, which means it increased, right? Because it went from 0 to some positive value because capacitor, or the charge on a capacitor, we just talk about the positive charge. And so it increased. And if I was reasoning this out, I might invoke an equation. Because I know that when I went from 0 to 1.5 volts on the battery, I went from 0 to 1.5 volts across the capacitor, right? And I know the equation for capacitance, any equation for capacitance, is charge over potential difference. Or charge per volt, right? And so, if I'm keeping my electric potential difference the same because it's connected to the battery, then when I increase the... Wait. This is wrong. It's not wrong. I can write it like this, right? Wait, am I? Yeah. I went from 0 volts, I increased delta... Oh my gosh, what's wrong with my brain? Oh my gosh. I increased delta V. This one's done. And so I must therefore have an increased Q. Right? Now that's equation form, but what you can also say is, well, obviously when I turn on the voltage here, I have potential energy in the electrons within the battery. So they get forced by the Coulomb force onto the negative plate. They get forced off of the top plate, right? So that by its very nature builds up charge. So you can, if you can explain that in words, that's fine. You can probably more succinctly explain that with the equation, but that's up to you. The electric potential, we've already answered that, right? When you increase the potential on the battery, then charge will flow until the electric potential across the capacitor is the same.
It's like as voltage increased, how did these quantities change? How does voltage increase as voltage increases? Or how does voltage change as voltage increases?
Oh. No, that what they're saying there, as the voltage of the battery is increased,
Okay.
the voltage of the capacitor increases as well. Yeah. That's kind of funny, but yeah, I see what you're saying. And then the electric field, as capacitor voltage increases, so does, the electric field obviously increased because there was no electric field before and there is now. And there we can invoke another equation because we know that the electric potential difference, the magnitude of it, is equal to the electric field times the distance d for a parallel plate capacitor because the electric field is constant. Right? It's that nice simple relationship. Technically, if I'm integrating in the same direction as the electric field, then it's going to have the negative in front. But you can pretty much get away with talking about just the magnitudes for the vast majority of what we're going to be doing with capacitors. Until we get them into actual circuits, then we need to be a little more careful. But here, if I know the electric potential across the capacitor goes up, then the electric field must go up because the distance didn't change. Right? So you can talk about proportions, you can talk about stuff like that. In any way, as long as you can get your ideas across, I know I didn't give you enough space there, that much space there. So as long as you can get your ideas across in that space and make it clear that you understand what's going on, then you're in good shape. Okay? So for the rest of today, you can work on this. We'll also work on it in class tomorrow. When it gets to the last part, you'll actually switch over to a light bulb where you can charge a capacitor. And then when you switch it, you can put the switch here. That discharges the capacitor. Notice that when I discharge or disconnect the capacitor from the battery and then I start moving it around, the charge literally cannot change, right? If it's connected to the battery and I start changing stuff, the charge on the plates can change. I can change the plate area. I can change how much charge I store on the plate. But if I disconnect it from the battery, there's no pathway to load more charge on or for charge to leak off. And so as I start changing things, it doesn't change. Understand that the electric field density represents the strength. So if I have something like this, notice the electric field density is not changing there. The electric field strength is not changing. The electric field is sigma over epsilon naught, right? So if the charge density doesn't change, which it's not here, you're changing the total amount of charge, but not the charge density, then the electric field strength is not going to change either. Okay.
I heart density.
What's that?
I heart density.
You all are fired. No, just you two.
What are you talking about?
You're being silly.
That kind of thing where it's like M over V and at the end makes like a heart with the V. I learned that in middle school.
So anyway, yeah. So capacitors will behave differently whether they're connected or whether they're disconnected, and then they're going to do something else when you use them to power a light bulb. Right? It's not going to behave like a battery, but it's going to do a similar thing as a battery would. Yeah.
If you store up that charge and then disconnect it and then just touch the two plates together, it's just
You get shocked.
Yeah.
Yeah. Did I show you guys this? This one?
Yeah. You should
Okay.
just,
This is a capacitor, right? And once the potential difference between the inside plate and the outside plate gets big, then you can actually have the spark go through the air. But if you just charge it up and then you just go like this, you would definitely get shocked, like pretty bad. So would you like to volunteer?
maybe. I'll think about maybe tomorrow.
Are you ditching school tomorrow again?
yeah. Just skipping.
All the way in Apple.
Yeah. Because
All right.
Everything's so great in Apple.
What's wrong with Abilene?
It's windy and
Hey, that's
nothing's
one of
there.
my
Oh, okay.
Yeah, it's always super windy.
All right. Bye, people at home.